Hi everyone, and welcome to the masterclass on building AI products. This is the first course, which is going to be focused on large language models or LLMs. But before we get into that, a bit about me. My name is Siddharth, and I've worked in multiple organizations across several industries, including across different roles like software engineering, data science, and more recently AI or Gen AI, and also across different industries from fintech, market research to the media landscape at the moment. I currently am based in Europe, but in the past I've also worked in India, that's where I'm from, and also in the US. I grew up in the Middle East, and I absolutely love to work with colleagues, team members, and learners from across the world. I'm really passionate about technology. I'm quite excited by all the amazing research and product ideas that are coming out with the help of AI and actually building solutions to solve real problems. And that's kind of what I want to channel through this course and help you learn along the way. I have also in the past authored a book which has been published by O'Reilly, also in the area of natural language processing. This was way back in 2020. So while the fundamentals are still correct, the way you would apply this to many of the problems in the book is vastly different. And that's kind of what we're going to look at today. Before we go into the course itself, I just wanted to give you an overview of the masterclass, which I have divided into 3 different courses. It's up to you whether you want to pick the entire masterclass or you want to focus on one or the other course. Both options are possible. In the first course, which is this session, we are going to really focus on large language models. So things like ChatGPT, Gemini, Llama, these things that you might have heard of. We help you understand it, make sense of it, and then build a product out of it. This product is called Narrative Tales, which is nothing but a personalized podcast generator. I find it really cool. I use it almost on a daily basis to learn about new subjects and topics. And yeah, definitely, it's quite amazing what you can put together. Course 2 is all about image generation models. So if you've heard names like Stable Diffusion, DALI, more recently Flux, and then this is all about understanding what goes behind these image generation models and how you can make use of them, how do you prompt them. And again, here the product that we're going to build is called Pod Picasso. And the idea here is that it generates cover art for any kind of podcast episode. So imagine your favorite podcast creators. They typically don't have the budget and the talent to create individual episode cover art for each and every episode. The larger ones typically do it, but not the small ones. And this is a product that can help automate a large part of this process. And in the process, we learn about what are image generation models. And course 3 is more focused towards deployment, managing AI products. AI products are quite complex to build, so like small prototypes are quite easy, and if you're using it for personal consumption, that's quite good. But if you're making this available to the public, then there are a lot of other things that go into it. For example, protecting against any injection. So the prompt injection is an important thing. How do you deploy this? How do you monitor whether the app continues to do what it does? Because prompts can be so, or the way the LLM responds or the image generation model responds to a prompt can vary a lot. So how do you ensure that it still sticks to the same quality? How do you evaluate? How do you monitor whether this is working as you expect? And what we're going to build here is something called as document. I'm sure all of us have written code in our life, and we will write code during the courses as well, but how do you keep this code up to date? How do you make sure that the documentation for this stays up to date and kind of conveys the idea correctly? And that's the sort of agent that we're going to build that will automatically create these documentation for our code for us. So those are the 3 courses. You can attempt each of them independently, or you can consider all of this as part of the masterclass and progress in this way. In this session, we are going to focus on the first course, which is all about large language models. Why are they important, right? So why are you in this course? It's because large language models have been seen as a transformative power, right? So if any of you have used ChatGPT, the way it responds, the vast variety of tasks that it is able to do is really very, very large, right from summarization to act as a companion to brainstorming, etc. There's really a lot that ChatGPT is capable of, including writing code and stuff like that. And that's what you see in all these magazine articles, that there's really some transformative power here. And therefore, our goal in this series is to basically understand what is really a large language model, what happens behind it, and sort of how do we make use of it? And that's why I really like this quote by Andrej Karpathy. For those of you who don't know, Andrej Karpathy is one of the stalwarts in the world of AI. He's worked at Tesla, he's worked at OpenAI. Before that, he worked at the DARPA Challenge and so on. And he says that the hottest new programming language is English. And the key part of this is that because it is English, it is language, it is communication, which a lot of us do automatically. It means that with just the help of English or communication, we can build AI products. And that's the power of these large language models. And that's what I want to show you in this course. And the way we're going to approach this is first, we try and understand what a large language model is. We try and understand what goes behind a large language model. How does it actually generate tokens? So you have a very strong fundamental understanding of what is actually happening under the hood. Once we have this, then we will actually use this information to build a really cool product. In this case, Bot Picasso. But it's important to understand first and to really have this fundamental core and then build a product using that. So you are going to apply what you learn. And when we talk about application, we are going to build things that have a real world use case. This is very important for me. And that's how I also set up many of my products. They're not just toy examples, but they are examples that you could build on and make an actual product. Many of past learners have actually done this, so built entire products out of this. But at the same time, it is still simple enough for you to make a start. So you don't need to get overwhelmed. We will provide you with a lot of resources and kind of boilerplate that helps you get started without much effort. And then you learn by iterating through this. And iterating through this means that you have a goal of what you want to build, and then you adapt the prompts and you adapt what you build in order to achieve that objective. And that's the whole learning process. And that's what these products help you to do. And at the end, it also needs to be fun. We want to build cool stuff that we can use ourselves, that we find very valuable. And I'm sure you will agree at the end of this course that, yeah, what you built is also really exciting. And I'm looking forward to how you apply it. One of my biggest takeaways whenever I conduct these courses is to look at the things that people have built, because the way you might apply it is very different from the way I might apply it. And that's the learning process that I also look forward to in this, right? So it's always a two-way process. It's not just, me talking and you learning, but also you sharing what you built and us learning together through the challenges you faced and also the interesting behaviors you identified and how you kind of adapted that to your use case. So I'm really excited and looking forward to seeing what all of you build in these courses. I want to give a brief idea of how you might approach this course. This is just a recommendation. It's not necessary that all of you have to follow this, and each person's learning style, as I have found, is different. But there are a lot of resources, and I just want to point a path or approach that you might take. The step one I would recommend is to watch the lecture videos. That is this video and the next one, which together roughly will be about an hour, which is me trying to explain the how a large language model works, what is happening under the hood, and so on. So this is probably a great starting point for you to really understand what an LLM is. Once you've done that, I would recommend that in the next step, you go through the course material that is there also provided to you. This is the attached PDF, which goes into a bit more detail into what the LLM is. It also provides additional resources, papers, blog posts that you can read, which kind of cements your understanding of what you saw in the first step. In the last step, this is where we go into building the product. And so Here again, there is the last video, which is again roughly about an hour, which is me walking through the notebook. And at the same time, this is where it starts to get a bit more creative. You can follow along with the video with the same notebook and kind of start adapting it right there. Or you can watch the video and then try and build the project yourself. And so this is really, yeah, based on your own individual learning style and so on. But hopefully this serves as a concrete approach for how you might use the various resources that are part of the course. Cool. So the rest of this session, we are going to really focus on the evolution of large language models. What are they? How did we get to where we are today? What has actually happened under the hood? That's kind of what we're going to cover in the last, let's say 20, 30 minutes, right? So this is a graphic from The Economist. I've linked in each of my slides. You will find the references below. So in case you want to read up further on it, you can do that. But on this infographic, what you're seeing on the x-axis is the time scale. So starting from somewhere in 1950 and going up to 2022. So you can see it's still not supremely updated. On the y-axis, what you're seeing is the estimate of how much compute it took to train a given model. And the model itself is, represented by a dot, and there are different colors of dot for different types of models. What is important to take away from this graph is the rate at which the amount of compute that is required to build some of the more recent innovations in AI compares with some of the AI models that came before. And an important thing for you to note is that the y-axis is actually not linear, but actually exponential. So you can see this is not, so it's going 10 to the power 4, 8, 12, 16. So it's really an exponential scale. So what you see here, it looks like a kind of graph that is going upwards, but in reality, it is growing like crazy. It's almost like a vertical line. And that's very, very important because this is the amount of compute that is required to train some of the more recent innovations in AI. So you see here, for example, names like BERT Large, which I would say is one of the first large language models, which came around 2017-ish. Then you have GPT-2, GPT-3, PaLM, which is a precursor to Gemini and stuff like this. And you can see all of them, really starting to get clustered on the top right over here. And why do they get clustered over here is because of various reasons. And that's what we're going to see below. So the key important thing to take away is that the most recent crop of AI models really have made use of a gigantic increase in the compute power. But is that only the case? And actually, no. So it's not just that the model size or the compute that is required to train that model changed, but also the way that you train these models changed, right? So that's what I say here by saying it's not just the model size, but also the way that you train these models has changed. So you start with more like traditional NLP techniques. Then you had the first BERT model, like I said, a precursor to a large language model, but there also you would work with it slightly differently. So you would do a fine tuning. And then you had these emergent behaviors like zero and few shot learning, instruction fine tuning, and then finally reinforcement learning with human feedback. So with each new model that came out, like GPT-2 to GPT-3 to GPT 3.5 and so on, it was not just keeping on increasing the size of data that it was trained on, the amount of compute that it was trained on, but also the way it was trained. And that's important to recognize because that gives us an understanding of what is really happening under the hood. And that's what we're going to cover in the next few slides. So let's start with the traditional world, right? So what I mean by the traditional world is the traditional NLP techniques. So whenever you're working with text, so for an example here, these are reviews that are coming from Amazon. So there are multiple reviews of a particular product. And let's say that you wanted to predict whether a particular review is positive or negative. Let's suppose that this was something that you were trying to do in the 2010, 2015 timeframe. The way you would approach this would be by creating a numerical representation of these texts, which is typically called as a bag of words approach. So for instance, what you see here in this blue table is that you have different words. Each column is a word. And against each column, so each row is then an observation. So an observation is a review in this case. And against each review, you would mark if that word exists in that review, you would mark it as 1. If the word does not exist in that review, you would mark it as 0, right? So this is just a snippet of the actual table. The actual table will be much longer because there are going to be a lot more words. But what you see is that it is nothing but a numerical representation of the text that is there in the review. So that's the step 1, to convert the textual representation into a numerical representation. And the process, the way it is done here, is something called as bag of words approach, or one-hot encoding, etc., etc. These terms itself are not important, but if any of you have worked with data science before, then you know what I'm referring to. But it's not very important to what we're doing, but just to give you a sense of how it would happen in the traditional world. Against each of these observations, you would also have a label, right? So is this a positive review? Is this a negative review? Something like this. And this is typically would have been done manually. So that means a human being would have looked at it and said, yeah, okay, that's a positive review, or that's a negative review, and stuff like this. So there is a human annotation effort that is required in doing this process. Of course, there are ways around this. For example, you might say, hey, actually, this person has given it 4 stars. So it's likely that they're happy with it, and it's a positive review. That may not always be the case, but you could also achieve this through some kind of proxies in this way. But typically you would have to actually create a data set. This is what that data set is. So the numerical representation of the text, and for each observation, there is a label that is associated with it. And typically this label would have been annotated by a human being, which means that there is a lot of human effort involved in doing this. And once you have this data set, now you would apply a machine learning algorithm. So machine learning algorithms include things like random forest, XGBoost, things like this. If you've heard about it, this is the algorithm that we would use. We would apply this algorithm to this data set, and then we will get a model that helps to predict whether the next review that comes in is actually positive or negative. So that's the way we would traditionally solve this problem, using techniques like one-hot encoding, bag of words approach, and stuff like that. But now let's move on to the next phase, where we talk about unsupervised training and LLMs. So here, there are 2 important things that really changed. On the left-hand side, you see that you can use the data itself to generate labels. So that means that what happened now is that you can see, for example, here, there is a quick dash fox jumps over the dash dog, right? So you add a mask to any sentence and you can sort of automatically generate labels and training data, right? So you change the task. In the previous case, you had to say, is it positive or is it negative? But now what you do is you change the entire task itself to not predict positive or negative, but you just try to predict missing words in a given sentence. And because you have the original sentence, you can easily mask it. So in this case, you mask this and you know that in reality it is brown. So you know what it should be, and you then try and ask the model to predict what it should be, and then you can compare the two and see how far it is or how close is it, and then keep adjusting it to kind of train it in this fashion. And this is called kind of like unsupervised training, because you are not necessarily spending any human effort to generate these labels. You just pick a sentence and mask some of these words, and then you know the word, so you already have the labels. This is not the same as predicting positive and negative, but we'll come to why this helps, right? So this is an intermediate step that will eventually go there. And now you can imagine that in the whole World Wide Web, there's really so much information in terms of text that you can crawl and get in this way, right? So the massive amounts of text that the internet already provides gives rise to a massive amount of training data, which is generated or which can be generated in this unsupervised fashion. So that's the first step that changed with unsupervised or when you move away from these traditional machine learning algorithms. Then on the second side, what you see is that you can now train massive neural networks. You could train massive neural networks because of the access to GPUs. GPUs are a certain kind of, so just like you have CPUs, GPUs are traditionally used for gaming and visual rendering and so on. But in 2012, there was this ImageNet competition where the first neural network algorithm called as AlexNet actually made use of GPUs for the first time to train neural networks. And that was really like a game changer, because then you could figure out that, hey, these GPUs, while they're great for gaming, they're also extremely good for training neural networks, and you could increasingly have really large sizes of neural networks. I've just given a simple representation of a neural network here. For instance, there is an input layer, then there's an output layer, and then there are hidden layers in the middle. And what you see as dots here are nothing but the weights of the neural network, which connect all these layers. And this weights is what we also talk as parameters, which is then determining the size of any model. So when we say that, for instance, GPT-2 had a parameter size of 175 billion, then that's the kind of parameter. What we're talking about is the weights or the number of weights that are there in such a neural network, right? So basically, the explosion of GPUs, or the capability to train large neural networks on GPUs, combined with the ability to generate massive amounts of data using this unsupervised approach, is kind of what got us to a large language model. It allowed us to train large language models in this way without much effort. And the first such large language model was called BERT, which is from Google. And this was, I would say, the first time that something like this is used. Now, if you remember in the last slide, we still spoke about predicting whether a particular review is positive or negative. And the way that you would now use something like BERT to do that is by saying, hey, let's take the BERT model. Now, this BERT model, because it has been trained in this fashion, already knows a lot about language. It already knows how things should, look, what word should come next. So it already has a lot of language information built in. And then I need to just create a very small data set, maybe 50 or 100 examples. So the amount of annotation effort is very low. Like 50 or 100 examples is something that maybe you can look at and easily create in an hour by saying, hey, it's positive, hey, it's negative. And then you would fine tune the last layer of a BERT model. So this last layer of the BERT model, you would fine tune for that specific task. What do I mean by for that specific task? It would be fine tuned on that 100 observation data set that you have just created. So this was the way that you would apply the LLM in the first place. The LLM, what do I mean by the LLM? In this case, BERT, right? So this was an order of magnitude improvement already from the traditional NLP techniques, because you don't then need massive amounts of labeled data for all your Amazon reviews and stuff like this. If you had 50 to 100 of it, you're already good to go, because you would then take the BERT model. The BERT model already knows a lot about language, and then you would just fine tune the last layer. That's what would happen. But then we go into the next step, which is what I call zero shot or few shot learning. And this was the first time. So that was the BERT model. And here we're talking about the GPT-2 model. This is a model that comes from OpenAI. And this was quite radical because they increased the order of magnitude of the parameters, right? So the BERT model had roughly 340 million parameters, and the GPT-2 model had roughly of the order of 175 billion parameters. So that's the order of magnitude of both GPT-2, GPT-3, roughly like this. And what they saw was, hey, these guys are now unsupervised multitask learners. So language models are unsupervised multitask learners. That was the title of the paper. What does it really mean? It means that you no longer have to do this last fine-tuning step. You could quite literally just take the examples that you have, put it directly to the model, and the model would learn to do what it has to do, right? So just to give you an example, if you look here, this is from the actual paper, all you had to do was give one example. So in this case, this is an English sentence, and this is the French translation of it. And then you can actually give it the French reference and the English translation, and then the model would learn, hey, that's what I need to do. And so the next time you give it either a French, then it'll give you English. If you give it English, it'll give you French. So with just a few examples, it really understands what is required to be done of it. There is no fine tuning. There is nothing else that you need to do with the weights itself, with the parameters. You can just directly give it the examples and it would do what you asked it to do. And that's what you see here in this example, where I gave it some examples of tweets. So I just said, hey, I hate it when my phone battery dies, etc., etc. And then in the last one, I said, okay, now I'm not going to say what it is. You tell me what it is. And then it knows that, that it needs to do sentiment prediction for tweets. And so it gives me the right answer. So this is called a few shot example. And there are also zero shot examples where you could directly ask questions of the large language model. And then you would say, okay, who wrote the book, The Origin of Species? Who is the founder? And you would actually get answers directly without it actually knowing anything and so on. It would not be correct all the time. And as you can see, there are errors here and stuff like this. But this was quite a revolutionary capability because you no longer had to even create that 100 observations and create that training data set. You could just take 2-3 examples, put it to the model, and the model would know what to do, right? So it's like really an unlock, I would say. But this thing still had issues because these models are trained on next token prediction, right? So all it is trying to do is saying these are all the words that came before, and then it tries to predict next. That's actually what it's doing. So it says, hey, these are the tweets. For each tweet, there is a sentiment. So it's likely that this is what I'm expected to do. And then I'm expected to say whether this tweet is positive or negative. That's what it would understand, or that's kind of how it would behave. But this obviously means then that when you ask it to do something, like when you give it a task, for example, what you see here is a prompt which says explain the moon landing to a 6-year-old in a few sentences. What you then see is that GPT-3 tries to complete it by saying explain the theory of gravity, explain the theory of relativity. So it is trying to just imitate. It is just trying to do token completion. It doesn't really understand that you've asked it to do a task. It just says, I'm a token prediction model. I just try to predict the next token based on the tokens that came before it. This is kind of what I predict. And that's not really good because this is very different from the ChatGPT one, where you can say, hey, please summarize this, or please answer this question. And then it understands and it does what it does, right? It gives you back the answers. And the way to achieve that is through the second step called as instruction fine-tuning. So what would happen in this particular situation is that you would take the base model, so the LLM, GPT-2 or GPT-3, and now you would fine-tune it with a particular data set. And this data set is called as the instruction fine-tuning data set. And again, I've linked the paper as always. You can see this. This is nothing but a data set that consists of a series of question-answer pairs. So for example, please answer the following question. What is the boiling point of nitrogen? And the answer is minus 320.4 Fahrenheit. Similarly, there are different ways in which you can frame these questions and so on, but for each question there is a corresponding answer. So you've created this question answer data set, then you take the base model itself and then you fine tune it so that it now understands that you need to understand the question and then generate the answer in this way. So in this process, what you're trying to do is helping the model to understand that you need to do question answering, that you need to understand this instruction and then answer in this way. And that's sort of what this whole process of instruction fine-tuning does. So the model then starts responding when you say, please summarize this or please answer this question. It knows that, hey, that's kind of what I'm expected to do, and then it generates the answer accordingly. It's no longer doing token prediction. I mean, it is still predicting the next token, but it now has been trained on several massive data sets of question answers, and so the next token that it predicts is based on the previous token. If the previous token is an instruction, then it knows that I need to answer that question, right? So that's kind of where the next token prediction is being adapted to also understand instructions and answer based on that. And this still has some limitations. This is still a bit far away from the ChatGPT moment. For instance, now, if you were to say, hey, ChatGPT is also quite creative. You can ask it to tell a joke. You can ask it to write a story. And, it does this reasonably well. I mean, you can always debate whether it's good or not, but at least it understands this instruction and does something. But many times there is an instruction data set that you can create for this, right? So like if I say, write a story about Lily, the doll and her friends, it's very hard to create a data set for this because if you ask a human being to write a story, they find it very difficult to create a data set for it. So just like how In the previous case, these are factual questions. So you can actually create an answer, or you can create a data set that has a question and answer. And so this is relatively easy. But when you're talking about creative tasks and so on, this is very difficult to do. So there isn't an instruction fine-tuning way to do this. And also what you're trying to do is generate text that is more likable to human beings. The way ChatGPT responds, as you might have noticed, is sort of very much like a human being. Like you feel like, oh, there is somebody there. Or it could be, the way a human being kind of writes responses and so on. And the reason for that is because of this technique called as reinforcement learning with human feedback. And what happens in this step, again, this is from the paper and you can read the blog post as well, is that there are many data sets or questions where you don't have, it's not possible to create a data set for it. So what happens is you give the task to the model, you ask the model to generate a response, and not just one response, but let's say 4 or 5 responses, right? So the same prompt, you ask the model to generate different responses. So you get 4 responses. Now you show this prompt and the 4 responses to a human being, to an annotator. And then you ask the annotator to rank these based on which one would they like the most and which one would they like the least. So that's what you see here. So explain the moon landing to a 6-year-old, you generate 4 responses, A, B, C, D. This is coming from the model itself. But now the labeler ranks the outputs from best to worst. And again, you create a large data set based on this, and then you use this data set to train what is called as a reward model. And this is not going into too much detail here because this goes into the direction of reinforcement learning, which is a whole area in itself. But basically, with this data set, you now try and guide the behavior of the large language model to generate responses that rank higher based on the human preference data that you have, right? So what you have created here is human preference data, where it says, hey, amongst these 4 responses, I like this the most, I like this the least. Now do this multiple times, get a lot of annotators to look at it, you create a large data set based on this, and then you use this data set to then train a reward model, which rewards the LLM for generating text that is more likable to human beings, and to punish the model when it generates text that is less liked by human beings, right? So that's the difference between this. And this is called reinforcement learning with human feedback. So the way you would do it is called reinforcement learning, and you're using human feedback because you're using manually annotated data from human beings. And in this way, you then train the model now again to kind of generate responses that are actually liked by human beings. That's the goal. So this was the third and most important step that gets us to the ChatGPT moment. And so now if I summarize all of this, what you see is that there are a lot of different training steps that got us to where we are today. In the first step, that there is world knowledge, right? So you train these massive large language models on the entire data set of the internet. And this was made possible because you had massive amounts of GPU on the one hand, so you could train large neural networks. You had massive amounts of data on the other hand, scraped from the internet. And then you didn't need to manually label this because you could easily mask tokens and therefore just do next token prediction. So this allowed us to create and train large data sets, so large language models using large data sets. The second thing is you then had to do an instruction fine-tuning data set, because otherwise at this point it would just do token completion. But if you then train it to understand instructions, you could then give it tasks, give it commands, and the LLM knows what it needs to fulfill. So that was the second step. And then the third step was aligning with human feedback, which we just saw, which is to kind of train the model to generate text that is preferred by human beings. So when you put all of this together is where you get ChatGPT, where you can say, explain the moon landing to a 6-year-old in a few sentences, and that's what you get. But you can then also say, explain the moon landing to an undergraduate student in a few sentences, and it adapts it, right? So it is understanding instructions. It has world knowledge about what is the moon landing, and it also generates it based on something that I would like, or that an undergraduate student would like, or that a 6-year-old would like, right? So it has also been aligned with human feedback. So It's very important to know this because the journey towards ChatGPT includes a lot of advances, and that's just the idea of here to kind of say, okay, there's really a lot that happened here, and that's where we are now. In the next session, what we are going to do is go further, so dive one step more to actually see how LLMs generate text and what are the techniques that they use to generate text. So that's in the next session.